We're going to move on to week 2, week 2B, which is the second week in the second semester, second quarter. And we're going to be talking about statics and static equilibrium. And before I go into the actual problems, there are two things about statics that we have to remember, two what they've called in the book conditions of equilibrium. And the first of these conditions of equilibrium equals 0, which means that all the forces in the x vector and all the forces in the y plane or the y vector have to balance out, so that because the definition of statics is the fact that there's no motion. The second is, and this is the new understanding, is that the net torque, which is delineated by this, also has to be equal to 0, otherwise there would be motion. Now torque, and this is a formula you might want to put on your next card, is equal to the force times the sine of theta times the distance r, or the radius in this case of the torque. So if you have a force that's applied at a distance from a pivot point, r is this distance, and the angle at which the force is applied is theta, and the force being there. Now another thing is that you have to be very clear where the pivot point is. And where the pivot point is not the same as, is not a consideration when you do this aspect, this first aspect of equilibrium. It is only important when you're calculating the torque. And so with those introductory comments, I want to move on to talk about the problems that we're working on this week. And the first of these problems is problem number 1. And it states, when opening a door, you push on it perpendicularly with a force of 55 newtons at a distance of 0.85 meters from the hinges. What is the torque you are exerting relative to the hinges? Now they've told you the pivot point is the hinges, and here's the door and the force, and they tell you that that's perpendicular, so that the angle of application here is 90 degrees. Now the reason that's important is the sine of theta in this case is 1. Therefore the torque is simply going to be equal to the force applied times the distance, which is 55.0 times 0.850. And the answer to that is 48 or 46.8 Newton meters. And Newton meters is the SI unit for torque. Part B says, does it matter if you push at the same height as the hinges? And the answer to that is no. Where in the y-axis, or in this case because it's coming out of the board and into the board, where in the z-axis you apply your force has no impact on the torque that's being exerted. Number 2, when tightening a bolt, you push perpendicularly on a wrench with a force of 165 newtons. And again, they tell you perpendicular, so the sine of theta, again, is going to be 1. And the distance is 0.140 meters from the bolt. And the bolt is the pivot point. If you were to draw this, here's the bolt, and here's the wrench on the bolt. And so the pivot point is here, the distance is here, and the force is being applied. And so, again, the torque here is going to be simply 165 times 0.140. And that makes this fairly simple. It says, how much torque are you exerting in Newton meters relative to the center of the bolt? Okay, the answer to this, if you multiply this out, is 23 0.1 Newton meters. Now they ask for the same answer, but they ask for it in foot-pounds. There's two ways you can do this. You can basically say, okay, you have 23.1 Newton meters, and so 1 meter is how many feet? It turns out it's 3.28 feet. And 1 Newton is how many pounds? And it turns out that 1 Newton is, well, it's actually the better way to do it, the better way to do it here is to say that 4.45 newtons is equal to 1 pound. If you multiply by 3.28 and divide by 4.45, you get 17.0 foot-pounds, which is the English unit for torque. 17.0 foot-pounds of torque. Now the other way you can do it is you can actually just look up how many foot-pounds there are in a Newton meter, and it's whatever 3.28 divided by 4.45 is. And that's the other way you can do it. Number 3 states that 2 children are on opposite sides of a door playing, and both are pushing horizontally and perpendicularly on the door. One child pushes with a force of 17.5 meters, so child number 1 pushes with a force of 17.5 newtons, and the second at a distance of 0.6 of a meter, so R1 is equal to 0.00600 meters, and the second child pushes a distance R2 of 0.450. Now they're pushing on opposite sides, so what force must this child be pushing in order to counterbalance and prevent motion? And so the net torque here is going to be 0, so that means the torque exerted by number 1 child has got to equal the torque exerted by the other child in opposite directions. Now if you want to get into signs, you can say that clockwise, a torque that results in clockwise motion is positive, and negative motion, or counterclockwise, is negative. Or, I mean, there's a lot of different ways you could do it. Or you could just say this has to be true for the net to be equal. And so that 17.5 times 0.600 has got to be equal to F2 times 0.450. And so you bring this over. If you divide this by 0.45, you get what F2 ends up being. And so if you do the math here, you get 23.3 newtons. And so the second child has to push harder because the pusher is closer to the hinge than the person pushing at 17.5 newtons. Number 5 states the following. It says for you to look at the seesaw problem, example 9.1, and you say that the center of mass of the seesaw is 0.10 meters to the left of the pivot on the side of the lighter child, and assuming the mass of the seesaw is 12.0 kilograms. The other data given in the example is unchanged. Explicitly show that you follow the step blah, blah, blah. That's not really that important to me. But if you repeat this problem, what you're trying to find is the distance that the larger or the smaller child or the larger child is from the pivot. So let's draw it first, which is what I usually do. And the pivot point is closer to the larger child. The larger child, we'll call the larger child F2. And this distance we want to find is R2. The smaller child is over here, F1. This distance, R1, is equal to 1.60. And the larger child weighs 26.0 kilograms. Has a mass of 26.0 kilograms. Now what they've added here is the fact that the seesaw has a mass of 12 kilograms, and that mass is 0.16 meters from the pivot point. Now, these two torque have to equal this torque for it to be, these are the two torque that are moving in the clockwise direction, and they have to be equal to the single torque that's moving in the counterclockwise direction for this seesaw not to move. So you can write this two ways. You can write 0 equals F1 R1 plus F2 R2, or excuse me, let's call this W, the weight of the seesaw, times 12.0, and plus, and then this one is is clockwise, so we'll call this negative, and this negative, and this one has to be clockwise, so this is F2 R2. The other way you could do it is to say that the distance this way is positive and the distance this way is negative. It doesn't really matter just as long as you do one or the other. The other way to do it is to say that anything on this side has to equal everything on this side, so that F1 R1 plus W times 0.610 is equal to F2 R2. Now I'm going to do something here because all three of these, to get the forces, you have to multiply all three of these by 9.8. If you divide through by 9.8, you can just use the masses. So you can say 26 times 1.60, 26.0 times 1.60, plus 12.0 times 0.160 is equal to, and the larger child's mass is 32.0 kilograms times R2. And if you do the math here, add these two together and then divide by 32, R2, comes out to be 1.36 meters from the pivot. One more problem before we move to a new video. We'll do number 6. Number 6 states, suppose a horse leans against a wall as shown in the figure 931. So it's showing you in the figure. Calculate the force exerted on the wall, assuming that the force is horizontal, while using the data in the schematic representation of the situation. Note that the force exerted on the wall is equal and opposite to the force exerted by the horse, keeping it in equilibrium. The total mass of the horse and rider is 500 kilograms. Take the data to be accurate to 3 digits. And so if you were to draw a picture of this, basically you have this horse leaning up against the wall, and I actually put the arrow in the wrong direction because what we want to calculate is not the horse, but the force against the horse, keeping it from moving. And so we'll call that F2. And it is a certain distance, R2. And if you look at the diagram, that R2 is 1.20 meters. And the center of mass, so this is the force and the distance that force has to be done. Now, opposing that is F1, and F1 is the mass of the horse times 9.8, and it is a 0.350 from the wall. So that's R1. So the wall is right here. And so the force is exerted up here, and it's to prevent the horse from falling down. Actually, I drew it right the first time. And so it's causing, the force of the wall is causing a torque in the counterclockwise direction. The force of the horse is causing the wall to go in a clockwise direction, and these two have to balance each other out. And since this is a force, we have to keep the 9.8 in here. So what you have is F2 times 1.20 is equal to the weight of the horse, or F1, times 0.350. And so that's going to be 500 times 9.8 times 0.350. And we can divide that by this R, 1.20, and this will give us F2. And the answer here is 1,430 newtons. Now, depending on how you align this in terms of which one is positive and which one is negative, you can say that because this distance is positive, or because this causes counterclockwise motion, then this has to be negative. And this one causes clockwise motion, so this is positive. And so that's one way you can do it. You just have to show that you've taken into account that one force is opposite in sign to the other force in order for it to turn out to be canceling out.